In the spring of 1941, in the quiet coastal town of Christchurch, Dorset, an engineer named Donald Bailey was hunched over a table in the experimental bridging establishment of the British War Office. The room smelled of metal filings and damp paper, littered with rulers, bolts, and small steel frames no larger than a man's arm. At first glance, what he was building looked almost childish, a toy bridge assembled from miniature panels and pins. But Bailey's model had been carefully scaled. Every bolt, every joint represented a structural principle he believed could change the way armies crossed rivers. What seemed like a hobbyist's curiosity was, in fact, a precise study in modular strength. Bailey's experiment was born from the grim lessons of the early war years. In France, the British Expeditionary Force had seen entire offensives stall because a single bridge had been destroyed. Heavy pontoon systems were cumbersome, and traditional truss bridges required cranes and days of work. The Royal Engineers had repeatedly found themselves stranded on riverbanks, surrounded by wreckage that they had neither time nor machinery to rebuild. Bailey, a civil servant in the Ministry of Supply and a former draftsman with an obsession for practical simplicity, wanted to replace the fragility of improvisation with a methodical design, one that soldiers could assemble with their own hands, under fire, using nothing more than muscle and precision. When he presented his idea to the War Office Committee, it did not command immediate respect. The room was filled with senior officers, many of whom still believed that bridging operations belonged to specialists with cranes and riveters, not to infantrymen with spanners. Bailey's tabletop model, however, had a silent defiance in its proportions. The panels, though small, interlocked perfectly, forming a lattice that grew stronger the more sections were added. He demonstrated how identical units could be bolted together in varying combinations, forming bridges of different lengths and load capacities. The engineers who tested it lifted one of the miniature spans, placed weights across it, and watched as it held. The structure bent slightly but did not fail. Bailey noted this with quiet satisfaction. In a full-size bridge, that subtle flexibility would prevent catastrophic collapse. The simplicity of the system was its greatest heresy. To the traditionalist mind, a bridge strong enough to carry tanks should also look monumental: massive beams, heavy rivets, and deep foundations. Bailey proposed the opposite: light, standardized panels, built not by a few specialists but by dozens of soldiers working in rhythm. His bridge could be launched forward on rollers, pushed over a river like an unfolding machine, and fixed into place without a single crane. It turned engineering from a construction problem into an assembly process. That shift in thinking was as revolutionary as any new weapon. For Bailey, it was not about personal recognition. He had spent his life buried in drawings and equations, more comfortable in the quiet of workshops than in the hierarchy of the army. Yet he understood that the war demanded ideas that could multiply effort, not just strength. He knew that every destroyed bridge in Europe was a delay measured not in hours, but in lives. His design was an answer to that arithmetic, a modular, repeatable act of repair against the chaos of destruction. In the months that followed, the prototype was tested under increasing loads. Panels were built at full scale, and Bailey's small workshop in Christchurch became the proving ground for a new kind of warfare logic, one that favored adaptability over grandeur. The bridge withstood the passage of a Churchill tank without deforming beyond tolerance. It was light enough to be carried in sections on the back of a truck, strong enough to hold a convoy of tanks, and simple enough to be assembled by men who had never studied engineering. Yet even with such results, skepticism lingered. To some officials, it was too easy, too elegant, too unlike the massive steel trusses they trusted. The report from the initial demonstration was filed and set aside, labeled as of interest but requiring further evaluation. Bailey left the hall that day without applause. He had built something that worked perfectly, but perfection was not enough without the blessing of bureaucracy. 3 years later, when Allied armies rolled across Europe, those same panels, once dismissed as a novelty, became the backbone of their advance. They carried tanks over rivers in Tunisia, Italy, and Normandy, assembled by exhausted men who needed only bolts, wrenches, and the memory of a precise pattern. The bridge that had been rejected as too simple turned out to be the simplest expression of victory itself. At that moment in 1941, however, no one could have known. There was only an engineer in a small English workshop, building a bridge from thought and patience, unaware that his creation would one day connect not just two riverbanks, but two eras of military engineering. His quiet persistence in that modest room marked the beginning of a revolution in how wars were fought, not through destruction, but through the ingenuity of rebuilding. From the earliest days of the Second World War, the problem of mobility haunted every Allied commander. The rapid movements of armored divisions, which had defined the German blitzkrieg, exposed a weakness in the Allied system that was as old as warfare itself: the inability to cross destroyed bridges quickly enough to maintain momentum. Each river, canal, or ravine became a potential trap, halting entire divisions for days or weeks. Bombing raids, artillery fire, and retreating enemies left behind a landscape littered with wrecked spans and twisted steel. Roads were useless if they ended at a gap that no truck or tank could cross. It was not the lack of courage or equipment that slowed armies, but the absence of a reliable way to rebuild what had been lost. By 1940, this weakness had already turned into a strategic disaster. During the retreat to Dunkirk, British and French engineers watched bridge after bridge collapse in flames. Columns of vehicles and artillery pieces were abandoned simply because the crossing points ahead had been destroyed faster than they could be replaced. Even when pontoon bridges were deployed, they demanded long hours of labor and fragile materials that could be torn apart by current or shellfire. Wooden trestles were easy to build but could not bear the weight of tanks like the Matilda or the Valentine, and permanent truss bridges required cranes, rivets, and calm conditions that war rarely provided. The German advance had shown that speed itself could be a weapon. When tanks moved faster than the enemy could rebuild, they shattered the rhythm of defense. For the Allies to counter that, they needed their own kind of mobility, not just in vehicles or fuel, but in the ability to keep the army's arteries open. Every delay at a river crossing multiplied through the chain of command: infantry waiting for supplies, tanks waiting for fuel, and medics waiting for evacuation routes. A single missing bridge could immobilize thousands. The rhythm of modern warfare demanded solutions measured not in days but in hours. Engineers faced a paradox. The stronger the bridge, the heavier and more complex it became to build. The lighter and simpler it was, the less it could carry. In theory, an ideal bridge would combine both strength and mobility, but no existing design achieved this balance. The British Army's standard equipment, the Inglis Bridge, a relic of the First World War, was too cumbersome and limited to small loads. Heavy mechanical equipment, such as cranes or large pontoons, could not be transported quickly across bombed terrain. The United States and France faced similar issues. Each nation had engineers capable of constructing marvels of steel, but none could build something that could follow the front line in real time. Behind every stalled offensive was a logistical crisis invisible to the public. The newspaper headlines spoke of battles, but engineers knew that victory often depended on 100 meters of missing roadway. When rivers flooded, when demolition charges cut the last crossing, or when the enemy's retreat left only craters and mud, the entire advance came to a standstill. Commanders demanded miracles from their sapper units: bridges strong enough to carry 40-ton tanks, light enough to assemble by hand, and simple enough to construct at night, under fire. Such demands sounded impossible, yet they represented the reality of the modern battlefield. In North Africa, these challenges became painfully clear. British and Commonwealth forces pursuing the Afrika Korps across the desert faced wadis, dry riverbeds that turned into torrents during sudden rains. Traditional bridging equipment sank into the sand or cracked under heat expansion. In Italy, mountains and rivers cut the landscape into segments, each demanding a new crossing. Every delay in building one meant fuel shortages, trapped convoys, and broken supply lines. The same pattern repeated in Burma, where monsoons washed away wooden structures faster than they could be repaired. The war had grown global, but the problem remained the same everywhere: mobility was the measure of survival. By 1941, the British War Office understood that the Army needed a new philosophy of engineering. No longer could bridges be unique works of craftsmanship, designed for one location and built by a few specialists. They had to become products, modular, mass-produced, and standardized across continents. A bridge should arrive at the battlefield like ammunition, ready to be used by anyone trained to follow a manual. It had to fit on the back of a truck, withstand tank loads, and be assembled by men working with wrenches instead of cranes. It was within this crisis of speed and logistics that the search began for a new kind of solution, a bridge that could turn chaos into order. The armies needed not just steel but a system, a repeatable design that could restore movement wherever destruction had stopped it. For the Royal Engineers, this was more than a technical challenge, it was a question of doctrine. How could a modern army remain mobile when every victory required rebuilding the world it had just torn apart? That question hung over every war office in London by 1941. The need was urgent, the materials were scarce, and the front was expanding faster than the engineers could plan. Somewhere between desperation and invention, the next step in military engineering was waiting to be found. It would take a mind capable of seeing bridges not as monuments, but as patterns, a modular rhythm of panels, bolts, and patience. And in that need, the problem that had halted armies would give rise to a solution that would carry them across continents. By the middle of 1940, the British Army had learned a painful lesson about the limits of its engineering doctrine. The old systems designed during the First World War had not evolved to meet the speed and mechanical power of the Second. The standard Inglis bridge, a relic of the previous generation, could barely handle the weight of modern tanks and required heavy lifting equipment to assemble. Britain's expeditionary force, after the retreat from France, found itself forced to abandon vehicles, not for lack of courage, but for lack of crossings. When the evacuation from Dunkirk ended, military planners realized that the army could not fight the next campaign without a new kind of bridge, one that could keep up with armored warfare. In the summer of 1940, the War Office created a program to search for a universal bridging system. The task fell to a small division within the Ministry of Supply known as the Experimental Bridging Establishment, EB, located in Christchurch, Dorset. The EB had been founded before the war as a research center for military engineering, but now it became a factory of urgency. Its grounds were filled with test frames, metal girders, and tanks used to simulate loads. Civilian engineers worked side by side with Royal Engineers, measuring flexion, weight distribution, and the time needed for assembly under combat conditions. The challenge was clear. A bridge had to be strong enough to carry a 40-ton tank and yet light enough to be built by men without cranes. Among the engineers assigned to this effort was Donald Bailey, a reserved civil servant in his early 40s who had spent years designing road structures and studying load distribution. Unlike many of his colleagues, Bailey had no military background, but he possessed an instinctive understanding of modular design. In his free time, he built miniature bridges using Meccano sets, testing how small components could be connected to create large and flexible frameworks. What others considered a hobby became the foundation of a radical idea, that the strength of a bridge did not depend on the size of its parts, but on the precision with which they could be repeated. Bailey's approach was different from the complex truss bridges proposed by traditional engineers. He imagined a system built from standardized panels, each light enough for a small team of soldiers to carry, and each identical in form and function. These panels could be bolted together on site, forming longer or stronger spans depending on the need. Instead of welding or riveting, which required specialized labor, every connection would use bolts and pins that could be tightened with hand tools. It was not a single bridge design, but a flexible kit, a language of parts that could be combined to build whatever the battlefield required. In February 1941, after reviewing Bailey's detailed drawings and small-scale models, the Ministry of Supply authorized the construction of a full-sized prototype. The order came with an exacting deadline. The model had to be ready for testing by May. The EB workshops began to manufacture panels, transoms, and cord members according to Bailey's specifications. Each piece was built to tight tolerances so that any panel could fit with any other, regardless of where it was made. This principle of interchangeability, common in weapons manufacturing but new in military bridge building, became the cornerstone of Bailey's concept. By early spring, the prototype was ready for trial. The first test was held on the grounds of the experimental bridging establishment, using a shallow channel known as Mother Siller's Channel as the test site. Soldiers assembled the bridge according to the written manual, using only manpower and basic hand tools. When a fully loaded Churchill tank rolled across the span, the structure flexed but held perfectly. Observers recorded the deflection, measured the stress, and concluded that the modular design exceeded expectations. It had achieved the impossible combination of strength and simplicity. The War Office Committee, accustomed to grand engineering projects, viewed the demonstration with surprise. The bridge lacked the imposing appearance of older designs. It was skeletal, functional, almost industrial in its plainness. But it worked, and that alone was enough to draw attention. Reports from Christchurch described it as a promising development in prefabricated military bridging. For the first time, officials began to consider that standardization could replace improvisation. The success of the trial marked a quiet revolution in military engineering. In the following months, further refinements were introduced. Load classifications were standardized according to the Military Load Class (MLC) system, and tests were repeated with varying configurations: single truss, double truss, and triple truss for heavier vehicles. The results were consistent. The more panels added, the greater the strength. Unlike traditional bridges that required custom design for each site, the Bailey Bridge could be scaled like a mathematical equation. This predictability meant that field engineers could plan crossings in advance, knowing precisely how many panels, transoms, and decks were needed. The war had forced Britain into an age of efficiency. Factories began to prepare for mass production, while engineers documented every step of the assembly process. The experimental bridging establishment at Christchurch had become the birthplace of a new era in combat logistics, a place where the laws of physics met the discipline of industrial production. And at the center of it all stood Donald Bailey, whose unassuming demeanor hid the fact that he had just given the Allies what they needed most: a way to keep moving. The idea that had begun as a model built from toy parts had now passed its first true test. What remained was to see whether this bridge, born in a quiet workshop on the English coast, could survive the brutal test of war itself. By late 1942, the war had outgrown the pace of bureaucratic approval. While engineers in Britain continued to refine designs and prepare manuals, the reality of combat was changing faster than any committee could adapt. In the deserts of North Africa, the British Eighth Army was locked in a relentless contest of movement against Field Marshal Erwin Rommel's Afrika Korps. Every mile of advance demanded roads, water, and above all, bridges. The desert seemed flat, but it was cut by deep wadis and seasonal rivers that became torrents after sudden rains. Each crossing could halt a column of tanks, and every delay risked giving the enemy time to regroup. The war that had begun as a contest of firepower had become a race against geography itself. For the Royal Engineers, this theater exposed every flaw in existing bridging equipment. The Old English bridges, with their heavy tubular frames, proved nearly useless in the shifting sands. Timber was scarce, steel was limited, and the logistics of moving cranes or pontoons across hundreds of miles of desert were impossible. Improvised crossings built from scrap and fuel drums collapsed under the weight of armor. Commanders began to demand something that did not yet exist: a portable, strong, and modular system that could be assembled anywhere, by anyone, under fire if necessary. By the autumn of 1942, the Bailey Bridge had already been standardized in Britain, but it had not yet faced combat. Factories in England and Canada were producing sections, and training manuals were being distributed to field companies. Still, many officers viewed it as an experiment. The decisive test would come not in a laboratory, but in Tunisia, where the British First Army advanced after Operation Torch. The rugged terrain, marked by rivers like the Majerda and its tributaries, presented an ideal but dangerous proving ground. In late November 1942, orders reached the 237th Field Company of the Royal Engineers to establish a crossing near Mejaz el-Bab, a small but strategically vital town west of Tunis. The Germans had demolished the existing bridge during their withdrawal, leaving the advancing British units stranded on the opposite bank. The situation demanded immediate action. Supplies and reinforcements could not move forward until a new bridge was built, and enemy artillery threatened to pin them down if they remained stationary. It was the exact crisis Bailey's design had been meant to solve. The 237th Company unloaded crates containing the new prefabricated panels, transoms, and chord sections, the first Bailey components to reach an active front. The men had trained briefly in assembly techniques back in England, but none had yet built a full bridge under combat conditions. Working in teams, they began laying rollers and launching the bridge section by section across the river. The system's modular design proved its worth instantly. Panels locked together without tools beyond spanners. Each completed section slid forward on rollers as the next was assembled. Enemy fire erupted from the far bank as the work continued. The engineers kept building through the night, relying on floodlights covered with canvas to dim the glow. Under ordinary circumstances, a crossing of such size would have taken days. The Bailey system allowed it to be completed in hours. By dawn on November 26, 1942, the first combat Bailey Bridge in history spanned the Majorda River. Its steel deck rang with the sound of tank tracks as vehicles of the 8th Army rumbled across, resuming their pursuit of the retreating Axis forces. Reports from the field described the event with understated precision. Bridge constructed overnight under intermittent fire. Performance satisfactory. Load class exceeded expectations. Behind those few lines was a transformation in military engineering. The Bailey Bridge had not merely worked, it had proven itself in the most unforgiving environment possible. It required no cranes, no specialized tools, and no heavy transport. Every component fit within the capabilities of ordinary soldiers, and the structure carried a tank column before the engineers had even dismantled their temporary supports. News of the success spread quickly through the Corps of Royal Engineers and back to London. Within weeks, demands for Bailey equipment surged across multiple theaters. The War Office issued directives to expand production, and new field manuals were rushed to print. The bridge that had once been dismissed as a toy now had the endorsement of battle. Its performance in Tunisia became a case study in adaptability, a design conceived in peacetime laboratories that had survived its baptism of fire. The crossing at Medjez-el-Bab marked a turning point not only for the bridge but for military logistics as a whole. It demonstrated that engineering could be as decisive as firepower, that control over movement was as vital as victory in combat. For the first time, the Royal Engineers possessed a system capable of restoring mobility to a modern mechanized army within a single night. The Bailey Bridge had moved from prototype to doctrine, from idea to instrument. In that moment, the war gained a new kind of weapon, one made not of explosives, but of precision, patience, and steel. And for Donald Bailey, far away in England, the news from Tunisia confirmed what he had always believed, that simplicity, when properly engineered, could change the course of a campaign. The design of the Bailey Bridge was the product of a precise balance between engineering logic and battlefield necessity. From the beginning, its purpose was not to impress with grandeur, but to function under pressure. Every dimension, every bolt, and every hole had been calculated to create a structure that could be both portable and strong. Each component was standardized so that it could be replaced, extended, or reinforced without redesign. It was a philosophy of modularity, an idea that a single repeated element, when properly joined, could achieve limitless combinations of strength and length. The main structural unit of the bridge was the panel. Each one measured 10 feet in length and 5 feet in height, constructed from welded high-tensile steel angles and cross-bracing members. Weighing approximately 270 kilograms, a panel could be lifted and carried by 4 soldiers using simple handles built into the frame. The dimensions were deliberate, wide enough to ensure rigidity, but small enough to fit inside the back of a standard army lorry or on a railway flatcar. These panels were the language of the bridge, the repeating symbols from which an infinite variety of spans could be built. Assembly required no welding or cutting in the field. The panels connected using standardized bolts and steel pins that locked into place with a hammer blow. The bridge could be built in single, double, or triple truss configurations, depending on the weight it was meant to carry. Each layer multiplied the load capacity. For light traffic, one row of panels on each side was sufficient. For tanks and heavy vehicles, engineers added more panels side by side or stacked them vertically to form higher trusses. The design obeyed a simple mathematical relationship: the more panels added, the stronger the bridge became. On the ground, the process was methodical. Engineers first laid a launching bay on one bank, a temporary framework of rollers and trestles. The bridge began to take shape horizontally, its nose section, a lighter framework, extending forward to reach the far bank. As each section was completed, the men pushed it forward over the rollers, launching the bridge across the gap. When the far end touched the opposite bank, they removed the launching nose and secured the structure on bearings. The whole process could be completed in hours rather than days, requiring no cranes or scaffolding. It was an assembly line built on mud and rock, powered only by human labor and precision. The Bailey system was accompanied by a comprehensive manual that dictated every step of construction. The instructions were written in clear, almost industrial language, describing how many men were needed for each operation, what order the components should be added in, and how to calculate the correct load classification according to the Military Load Class (MLC) system. This standardization meant that engineers from different nations could build the same bridge in exactly the same way. It turned military engineering from an art into a process, a repeatable method that could be taught, practiced, and executed anywhere in the world. By 1942, the system had matured into its final wartime form. British factories such as the Darlington Bridge Company and Cleveland Bridge and Engineering began large-scale production, followed by Canadian and American manufacturers. The United States Army Corps of Engineers adopted the design under the designation Portable Panel Bridge, M1, and retooled its production lines to match British specifications. The panels, transoms, and stringers were interchangeable between Allied forces, ensuring that a bridge built with British components could be extended or repaired with American ones. This interchangeability was one of the greatest strengths of the design, turning the Bailey from a British innovation into an Allied standard. Each complete set of bridge components could fit into a few trucks and be assembled by a single field company. The average 80-foot span could be built in 6 to 8 hours by about 40 men. Heavier configurations took longer but followed the same basic rhythm. Soldiers learned to work in teams: panel carriers, pin men, bolt men, and deck layers, each performing their task with near-industrial repetition. What had once been an act of specialized engineering had been transformed into a military drill. Testing continued throughout the war. Engineers experimented with floating Bailey bridges on pontoons, adapting the design to river crossings too wide for fixed spans. They even created Bailey suspension systems for mountainous terrain, using cables and towers to extend its range. The core idea remained the same: flexibility through modularity. No matter the obstacle, the bridge could be adapted, rebuilt, or reinforced without redesign. The genius of the Bailey Bridge was not simply that it worked, it was that it always worked the same way. Its creators had distilled the complexity of structural engineering into a repeatable field process. Every panel, every pin, every deck plank was part of a system that ordinary soldiers could master and trust. The bridge became a physical expression of industrial modernity applied to war, standardized, reliable, and infinitely reproducible. When the Allies began to coordinate global logistics in 1942 and 1943, the Bailey system became the cornerstone of their engineering doctrine. Each division's field company carried sets of panels, transoms, and decking in anticipation of the next destroyed crossing. The kit had become more than a tool, it was a guarantee of movement. Wherever the army went, the Bailey Bridge went with it, packed in crates and waiting for the next river, ravine, or canal. It was, as one Royal Engineers report would later call it, the bridge that moved with the army. The true test of the Bailey Bridge began not in a laboratory but on the battlefields of North Africa, Italy, and Western Europe. After its debut across the Majerta River in Tunisia in November 1942, word spread quickly through the Royal Engineers and Allied Command. Reports described how the prefabricated panels had performed under live fire, holding the weight of tanks and trucks despite being built overnight. For the first time, engineers had a bridge that matched the tempo of mechanized warfare. It could be carried forward, assembled in hours, and launched under fire. What had begun as a British experiment in Christchurch now became a vital artery of the Allied advance. As the North African campaign ended and the Allies turned their eyes toward Italy, the Bailey system moved with them. The Italian peninsula was a landscape of rivers, valleys, and steep mountains, terrain that seemed deliberately designed to slow an army. Every destroyed bridge was a defensive weapon for the retreating Axis forces. But now, instead of halting at each obstacle, British, American, and Canadian engineers unpacked their steel panels and began to rebuild within hours. During the crossing of the Sangro River in November 1943, Royal Engineers and Indian Army sappers assembled one of the longest Bailey bridges constructed during the war, approximately 1,200 feet in total length. Spanning multiple piers, it carried tanks, artillery, and endless convoys of supply trucks into the heart of the German defensive lines. The bridge survived repeated floods and constant strain, becoming a symbol of endurance in the Italian campaign. The 8th British Army and the U.S. 5th Army used thousands of Bailey bridges during their push northward through Italy. Some were small footbridges across streams, others were massive, multi-span constructions over bombed-out gorges. In the mountainous terrain of Cassino and along the Liri Valley, the modular system proved its unmatched versatility. Under shellfire, in rain and mud, engineers built crossings in record time. It was said that the sound of hammering pins and tightening bolts became as common on the front lines as the rumble of tanks. The bridge had become a new kind of weapon, not destructive, but enabling. It gave the armies what they had lacked in 1940, continuity of movement. When the invasion of Normandy began in June 1944, Bailey bridges were no longer an experiment, they were a doctrine. Every assault division landed in France equipped with its own bridging sets. The planners of Operation Overlord had calculated that almost every major river and canal in northern France had been destroyed or mined by the retreating Germans. Without the Bailey system, the advance from the beaches would have stalled within days. Instead, engineer units followed closely behind the infantry, assembling spans across craters, rivers, and bombed-out culverts. They worked under constant artillery fire and aerial attack, often completing bridges overnight so that armored columns could roll forward at first light. At the Orne and the Vire, at Caen and later at the Seine, Bailey bridges carried the momentum of the Allied armies. Each crossing became a race between destruction and reconstruction. The bridges had to bear the heaviest loads of the war, columns of Sherman tanks, self-propelled guns, and trucks loaded with ammunition and fuel. Yet the modular frames held firm. Even when damaged by explosions or heavy use, panels could be replaced within hours. The same standard parts built in factories in Yorkshire or Montreal fit perfectly into bridges erected by American or Polish engineers on the continent. The U.S. Army adopted the Bailey design so completely that it became the backbone of their corps of engineers. They built thousands of spans across Europe, so many that by the end of 1944, some divisions joked they were marching on steel. Bailey bridges were also floated on pontoons to create temporary ferries across wide rivers. In Italy, Burma, and northwest Europe, they replaced hundreds of destroyed stone bridges, restoring rail and road traffic in places where no other system could be built fast enough. Perhaps the most dramatic proof of the bridge's reliability came during the crossing of the Rhine in March 1945. While airborne and amphibious forces established bridgeheads, engineers on the West Bank began assembling long Bailey structures to carry the flood of men and machines into Germany. At Wesel and Ries, entire floating bridges composed of Bailey sections were launched across the river, some exceeding 550 meters in length. The Blackfriars Bridge, as one of them was called, carried a continuous stream of trucks and tanks into the heart of the Reich. The river that had once marked an unbreachable barrier was now just another obstacle in a sequence of engineering tasks. For the soldiers who crossed them, Bailey bridges represented more than a feat of construction. They were symbols of progress and survival. To the infantryman trudging through mud or the driver guiding a tank across a trembling span, the lattice of steel panels was a sign that the way forward remained open. Each new bridge meant that retreat was impossible and advance inevitable. It was a reminder that war was not only fought by those who destroyed, but by those who rebuilt faster than the enemy could tear down. By the time victory was declared in 1945, more than 2,000 Bailey bridges had been erected across Europe alone, with countless others in Asia and the Pacific. They had carried every conceivable load, from jeeps to locomotives, and none had failed in service. For the Royal Engineers and their allied counterparts, the bridge became a symbol of quiet triumph, the triumph of design, discipline, and endurance over chaos. Its performance in battle had exceeded every expectation, proving that a structure born from simplicity could bear the full weight of modern war. The success of the Bailey Bridge transformed it from a British invention into a global engineering system shared across the Allied world. What had begun as a small-scale experiment in a Dorset workshop became, within 3 years, a cornerstone of military infrastructure from Europe to Asia. Its design, so simple in concept yet infinitely adaptable, made it an ideal candidate for mass production on an unprecedented scale. By 1943, the Bailey Bridge was no longer a national project, it was an Allied enterprise, uniting factories, soldiers, and engineers across continents under a single, standardized design. In Britain, the Ministry of Supply coordinated production through dozens of industrial contractors. Companies such as Darlington Bridge Company, Braithwaite and Company, and Cleveland Bridge and Engineering manufactured thousands of panels, transoms, and decking sections. Each component adhered to strict tolerances so that parts made in Glasgow would fit seamlessly with those produced in Birmingham or Toronto. The United States, recognizing the system's versatility, adopted it under the designation Portable Panel Bridge, M1. American steel mills in Pennsylvania and Illinois joined the effort, turning out vast quantities of panels identical to their British counterparts. Canada, with its thriving wartime manufacturing base, became one of the largest contributors, exporting fully equipped Bailey kits across the Atlantic. The bridge's design philosophy, standardization through precision, allowed it to be built anywhere. The Imperial and Allied armies across the world adopted the Bailey as their universal bridging solution. Indian Army engineers used it extensively during the Burma campaign, where rivers and monsoon floods cut through jungles and valleys. Australian sappers built Baileys across the islands of New Guinea and in the Pacific, where the bridge's modular structure proved invaluable in terrain that defied traditional construction. In every climate, under every condition, the system worked exactly as intended. It was the first truly global military engineering technology, an invention that transcended geography, language, and national method. In the European theater, Bailey bridges became so ubiquitous that they reshaped the very rhythm of military logistics. A divisional engineer company could now carry its own crossing capability wherever it went. The standard Bailey set could be packed into a few trucks, each labeled and loaded with identical parts. When a bridge was destroyed by retreating German forces, the sappers simply unpacked their kits, assembled a replacement overnight, and moved on. The combination of British design, American steel production, and Commonwealth manpower created an industrial harmony that reflected the Allied war effort itself, a partnership of innovation, manufacturing, and discipline. The system's influence extended far beyond the front lines. It standardized training, terminology, and even measurement across multiple armies. Manuals printed in Britain were reissued in the United States and translated for use by Canadian and Indian forces. Soldiers trained in one theater could be reassigned to another and instantly understand the process. The modular concept even inspired post-war military engineering doctrines, influencing later systems such as the Medium Girder Bridge, MGB, and the U.S. Standard Military Bridge. The Bailey became a blueprint for interoperability, the proof that industrial design could unify armies as effectively as political alliances. Some of the longest and most complex Bailey bridges in the war were built during the Italian campaign. The 1,200-foot span over the Sangro River in late 1943 became a symbol of Allied engineering prowess, surviving floods and bombardments while carrying an unbroken stream of men and equipment. In Burma, engineers built Bailey spans through dense jungle, where airlifted components were assembled on remote rivers with little more than manpower and ingenuity. Each successful crossing reinforced the bridge's reputation for reliability. By 1944, production of Bailey components had reached astonishing levels. Tens of thousands of panels were stored in depots across Britain, ready for shipment to France after D-Day. In Canada and the United States, entire factories were devoted to producing bridge kits in standardized crates. This logistical miracle meant that Allied armies could build identical bridges thousands of miles apart using the same instructions and parts. It was the embodiment of wartime industrial cooperation, a physical structure that represented the unity of purpose among nations. The influence of the Bailey Bridge extended into civil engineering as well. Even before the war ended, surplus components were repurposed for reconstruction in liberated territories. In France, Italy, and the Netherlands, local engineers used Bailey sections to rebuild transport routes and reconnect devastated cities. Its use in humanitarian and reconstruction efforts further cemented its reputation as more than a weapon of war. It was a bridge between destruction and renewal. By the end of the conflict, Bailey bridges had been erected by every major Allied army and had appeared on nearly every front, from the beaches of Normandy to the jungles of Southeast Asia. More than 2,000 major spans were built in Europe alone, with thousands more in Asia and the Pacific. They carried tanks, trucks, ambulances, trains, and sometimes even civilian refugees. Each bridge stood as proof that ingenuity could be standardized, that engineering could become a shared language of progress. In its influence and reach, the Bailey Bridge was a triumph not just of design, but of cooperation. It demonstrated that modern warfare depended as much on the ability to connect as to destroy. It linked not only riverbanks and roads, but entire nations, British ingenuity, American industry, Canadian logistics, and Indian labor working in concert. The bridge that began as a rejected prototype in a small English workshop had grown into the connective tissue of the Allied war machine, carrying the weight of an entire coalition toward victory. By the final months of the war, the Bailey Bridge had become more than a piece of equipment, it had become a symbol of Allied persistence. In March 1945, as the Western Front pressed toward the heart of Germany, the bridge reached its ultimate test at the Rhine. The river, wide and fast, had long been seen as the natural barrier of the Reich. When German forces destroyed every existing crossing, it fell to the engineers to rebuild the path into Germany itself. Across Wesel and Ries, British and American units launched massive floating Bailey bridges supported by pontoons and anchored against the current. Among them stood the Blackfriars Bridge, one of the longest of the war, stretching approximately 558 meters including approaches. It carried a continuous stream of tanks, artillery, and supply convoys into Germany, its steel panels vibrating under the weight of victory. It was the physical embodiment of the Allied ability to turn destruction into motion. When peace finally came, the Bailey Bridge did not disappear with the soldiers who had built it. Its simplicity, strength, and adaptability made it indispensable in the massive reconstruction that followed. Across ruined Europe, engineers from Britain, France, and the newly liberated nations repurposed Bailey sections from military depots to rebuild civilian infrastructure. In France and Italy, temporary Bailey crossings reconnected towns divided by blown bridges. In the Netherlands, they spanned canals still filled with wreckage from the retreating Wehrmacht. Many of these, temporary, bridges remained in service for decades, quietly carrying post-war traffic long after their intended lifespan. The bridge also found a second life far beyond Europe. As colonies and territories rebuilt after the war, the Bailey system became a tool for development. In India, where wartime engineers had already mastered its assembly, thousands of Bailey bridges were erected through the Himalayas, Kashmir, and Assam. In Burma and Malaya, they became lifelines during the monsoon seasons, carrying relief convoys across rivers that had no permanent spans. In Australia and New Zealand, surplus Bailey components supported rural construction and mining infrastructure. The same system that had carried armies into battle now carried communities toward recovery. Governments recognized its value as a permanent resource. In 1946, Britain's Ministry of Works adopted surplus Bailey materials for use in civil emergencies and infrastructure repair. Floods, earthquakes, and road collapses could be met with a bridge ready to deploy at a moment's notice. The Bailey became a part of peacetime logistics as much as it had been of wartime mobility. Its legacy in civil defense continued well into the Cold War, with updated versions used by both NATO and Commonwealth countries throughout the 1950s and 1960s. For his achievement, Donald Bailey received formal recognition from the British Crown. In 1946, he was knighted for outstanding service to military engineering. True to his character, he regarded the honor with modesty, describing the bridge not as a stroke of genius but as the practical answer to a clear problem. To Bailey, engineering was an act of order imposed on chaos, a way to make movement possible when everything else had been destroyed. His philosophy resonated deeply in the post-war world, where reconstruction demanded precisely that kind of clarity and efficiency. The Bailey Bridge's impact endured because it represented more than innovation. It embodied a shift in how humanity thought about building. It was not a monument of stone or a work of artistry. It was a process, a kit of possibilities that proved that strength could come from repetition, precision, and trust in design. Its components, standardized and interchangeable, anticipated the modular architecture and prefabrication methods that would define the second half of the 20th century. In that sense, the Bailey Bridge was one of the earliest symbols of modern industrial thinking applied to human recovery. Many of the original wartime bridges continued to serve long after the soldiers had gone. Some still stand today in Britain, Italy, and India, their steel frames weathered but intact. They have outlasted the circumstances that created them, carrying the everyday traffic of civilians who rarely know their origin. The quiet endurance of these structures mirrors the enduring spirit of the era that produced them, pragmatic, disciplined, and profoundly human. By the time of Bailey's death in 1985, his invention had been used in more than 100 countries and had saved untold lives in both war and peace. The bridge that once symbolized movement through destruction had become a universal emblem of reconstruction. Its panels, bolts, and trusses were reminders that even in the most chaotic times, the act of building, of joining two broken sides into one, remained the most powerful expression of resilience. The story of the Bailey Bridge was, at its core, a story about clarity triumphing over chaos. In an age defined by destruction, when entire cities were reduced to rubble and rivers became frontiers between life and death, one man's idea showed that order could still emerge from disorder. The bridge was not merely a product of steel and bolts. It was a demonstration that the power of human reasoning could outpace the speed of devastation. Where artillery broke, the mind repaired. Where war divided, engineering reconnected. The Bailey Bridge stood as proof that intelligence, applied with precision and restraint, could be stronger than brute force. In the mechanized violence of the Second World War, the bridge represented something paradoxical, a weapon of construction. It did not destroy, threaten, or conquer, yet it shaped the course of entire campaigns. Every span thrown across a river erased a line that the enemy had tried to draw. It restored motion to armies that might otherwise have been trapped by their own momentum. The simplicity of its design belied a profound idea, that victory in modern war depended not only on the capacity to attack but on the capacity to rebuild faster than destruction could take effect. Each panel carried with it the logic of continuity, a quiet assertion that progress could persist even in the midst of collapse. The Bailey Bridge also revealed the moral geometry of engineering. Its parts were standardized, interchangeable, and impersonal, yet through them flowed the collective will of thousands. Soldiers who had never met each other, from different nations and languages, built the same structures in identical ways. This unity of design mirrored the unity of purpose that defined the Allied cause. In an age of uncertainty, the bridge offered a rare constancy. It reminded the men who built it that precision was a form of discipline, and discipline itself was a kind of faith, faith in the idea that the world could still be measured, calculated, and repaired. For Donald Bailey, the bridge was never about heroism. He had not fired a weapon or led an army, but his work embodied a different form of courage, the courage to believe that logic could defeat chaos. His drawings, once dismissed as naive, proved that clarity of thought was a form of strength equal to any weapon. Each successful crossing, each river conquered not by fire but by calculation, was a testament to the quiet power of intellect in the machinery of war. In that sense, Bailey's achievement stood apart from the violence it served. It was an act of creation hidden inside an era of destruction, an affirmation that the mind could still impose structure on the unthinkable. The philosophical weight of the Bailey Bridge extended far beyond its military purpose. It represented a turning point in how humanity understood technology, not as a force of domination, but as a means of restoration. The war had shown the extremes of what machines could destroy. Bailey's Bridge showed what they could mend. It became a symbol of transition, carrying armies out of battle and into the age of rebuilding. Its endurance in peacetime, as it continued to serve for decades after the war, was a reminder that the same intelligence that designs for conflict can also sustain peace. The bridge also spoke to something universal in human nature, the need to connect. Beneath the technical precision and the logistical mastery was a deeply human impulse to restore what had been divided. A bridge, after all, is a physical expression of cooperation. It links two sides that were once apart. During the war, those sides were literal riverbanks. After the war, they became nations and generations. The Bailey Bridge, replicated across continents, was a reminder that progress often begins not with conquest, but with the simple act of crossing toward one another. By the end of the century, long after the war had faded into history, the outlines of Bailey's invention could still be found spanning rivers, valleys, and even the ruins of newer conflicts. They stood as silent monuments to an idea that had outlived the war itself, that human reason, when disciplined by necessity and guided by purpose, could transform destruction into movement and loss into connection. In the end, the legacy of the Bailey Bridge was not just in the steel that survived, but in the principle it embodied. It proved that simplicity, when born of understanding, could achieve complexity without confusion. It showed that strength does not come from the mass of metal, but from the harmony of parts. And it whispered one of the most enduring truths of modern history, that the victories that last are not those won by force, but those achieved through the steady, deliberate clarity of the human mind.